Okay, thank you very much, Yuri. And okay, let's get started with the program, with today's program. As you can see, we have a first lecture. We have still 5 minutes, so maybe I should spend some word of introduction. So the first speaker is Nicola Marzari. Professor Marzari is the chair of the Theory and Simulation of Materials group at EPFL in Switzerland, also known as TEOS Group, and also is the director for the National Center for the Computational Design and Discovery of Novel Materials, also in Switzerland, that includes lots of research institutions and groups and university in Switzerland for the, as the name says, for the computational design of materials. Nicola has a long career, so let me just highlight a few things. He has contributed significantly to both the Hubbard functional, the development of Hubbard functional and Koopman's functional. This tutorial is focused on, but also importantly, he is one of the main developers of maximally localized Fourier functions and beyond DFT electronic structure method in general, and also has contributed to the definition of implicit solvents from also DFT, electronic and thermal transport, and also ensemble DFT for molecular dynamics simulation, especially on metallic system, and also has contributed to the definition of some important high throughput platform for large-scale calculation. So this is just a few highlights of his long and well-known career in our field. So with this, I would leave the floor to Nicola to start the talk. So I think I can stop sharing my screen here. Hi, Nicola.
Hey, and welcome everyone. I start to feel seriously old when sort of, your own students or postdoc introduce you. Anyhow, great pleasure to be here. This will be a talk introducing a little bit the flavor of what will be, one of the core themes of this workshop about, the developments of Hubbard and Koopman's functionals. But I'll also start with a few words of introduction on the general field of electronic structure simulations. What I like, I think, when we started this, trying to get better energy functional and trying to get functional for spectral properties, I felt, we often talk about Jacob's ladder. I felt that we were trying to climb a mountain. This is K2, is the second tallest one in the Himalayas. And I like to think that, in Himalayan climbing, there are two styles, and there is the expedition style. And this is actually the Italian expedition that in 1953 got to the top of K2 for the first time in the world. And, absent Inuria Verbi, I feel this is what we tend to do with, diagrammatic methods. They are very powerful, but also very complex. And there is another way to climb mountains that is the freestyle solo climbing, pioneered here with Reinhold Messner, climbing without oxygen. And I think, the story of electronic structure has told us that, we can try to crack difficult problems with powerful and complex perturbative approaches. But I think the entire lesson from Walter Kohn and what followed is that sometimes there can be power in simplicity. And functional theory, in my opinion, have really their power in their simplicity. So with this, let me actually sort of give you an introduction here. Let me actually move this out of the way. In general, I've been doing first principle simulations forever. And, this is maybe my short list of the reason why these, are incredibly useful to both scientific discovery and technological innovation. Because, and you'll see, we use them to understand, predict, design materials, devices. Often they push us to suggest novel microscopic physical theories. I think just at the, Berry phase theory of electric polarization and orbital magnetization that came from the need to calculate properties. Because they, often can be very accurate, they can be used to support, streamline, and even inspire experimental efforts. And because they are basically based on, at the end, a computational infrastructure that, keeps progressing, even if our algorithms and codes were not to progress, they're really a very powerful or almost unique accelerator for discovery and innovations. And in fact, they are so prevalent these days that already 8 years ago, Nature listed the top most cited papers in the entire, say, scientific medical engineering literature. And in the top 100 most cited papers, the most represented field was actually density functional theory. 12 papers in the top 100, 2 papers in the top 10. If we focus on physics, this is from 3 years ago. I sort of do this every few years. The most cited paper in the entire history of the American Physical Society. You see the top 15 in red, or actually 18 out of 20 are all about the density functional theory, with a single one also on Hartree-Fock and Müller and Plessé. And so these are all the, if you want, theories and algorithms, but also sitting on this computational platform that, at least in the past 30 years, has been on a cycle where capacity doubles every 16 months. So when I started my PhD in 1993, up until now, we have actually had a 3 million-fold increase. And there is no other field in science that has seen this acceleration. So it's almost trivial to say that, 21st century science and discovery not only will greatly benefit, I would say, from computational science, but will be really driven from computational science. And computational quantum mechanics, you all know, is very powerful. I just show you a few fun examples here of the things that you can do. This is a project that we had here on predicting the color of materials. That really means understanding the interband and intraband electronic transitions that take place when a photon impinges on a material. And so basically understanding what is the dielectric response in the optical limit, and that means the reflectivity, absorption, and also color, and if you want, shininess. And the top is actually the computational prediction, and the bottom is what the experiment sees. But of course, the bottom proceeds at the speed of humans, at the speed of your physical infrastructure, while the top proceeds at the speed of computational infrastructure. So it's now much more inexpensive, and if you want, also much more fun to first explore with simulation and then do the experiments and check and figure out. Simulations are never perfect, and also many times they fail miserably, but in general, in those areas where they work and they're accurate, they are invaluable. Another example, say, talking about, I would say, multi-physics, multi-scale simulation. In this case, looking at the resistivity. Here it's a monolayer of graphene as a function of doping and as a function of temperature. And you see on the left the theoretical prediction, and on the right the experiments. So not only there is very good agreement, but you can actually understand what happens, why at low temperature different dopings give rise to different resistivity, why at high temperature it sort of converges, why there is a change of slope. In this case, which are the electron phonon scattering mechanism that are driving this physics. And lately, what has also become wonderful is that if we have accurate quantum mechanical data, we can use machine learning techniques, we can use neural network, we can use kernel regression methods to actually teach quantum mechanics to these technologies, and then use those instead of the direct quantum mechanical simulation. And this is already, I would say, revolutionizing the world of, say, structural functional materials, where you can, fit the potential energy surface of a neural network and then explore phenomena like here, say, the pre-melting of a metal surface at a time scale and length scales that would be completely out of reach to classical ab initio molecular dynamic simulations. And, these techniques can even be used to start and engineer materials that are very relevant to industry. This is an example of, say, patents that we have done with Solvane, finding optimal compositions and doping for solid state electrolytes. And the last sort of example, these are just taken from our own work, but just because I'm familiar with them, it's complementing experiments, like here looking at vibrational spectroscopies like CEIRAS, basically infrared, during electrocatalysis, and identifying what are all the different reaction products from the appearance of their vibrational peaks at different potentials. And one can match exactly what is the molecular structure with the spectroscopic signature. So, having said that, and probably you are all familiar with these ideas, there is a lot of enthusiasm these days about the idea that we can actually change not only the world of science, but the world of technology by, discovering novel materials or materials with novel properties by this combination of powerful quantum engines, machine learning, data to really achieve this goal of developing novel materials. And novel materials is what our society desperately needs. I mean, it's so easy these days to tell you how much, the availability of energy is critical to the well-being of 8 billion people. You need a lot of energy just to, produce the food that feeds 8 billion people. And the list is long, and it goes indeed from this key, I would say, sort of challenges for us of harvesting energy, converting, storing, being more efficient in using it, protecting the environment and repairing the environment from actually the damage that 8 billion people make, and try to make sure that, our society works and thrives. And not only that, but also having fun with it, having a new science, and often it's novel materials that really drive novel science. Okay, with this sort of, introduction of, in general, this world of, computational understanding, prediction, characterization of materials, let me actually focus the rest of the talk on this key topic one, that is, making sure that our calculations are actually accurate enough that we can believe them. And this is the three pillars, I often say, of material design and discovery. I will not discuss 2 and 3, but I'll just focus here on basically what has been maybe the longest challenge in our field. It started from the very first electronic structure calculations in the 1950s, 1960s, and it's still in general, a very difficult problem to crack. There are still a lot of complexity that are very challenging to handle. I don't want to give you the idea that we have done with, say, electronic structure simulations in materials. even just the complexity of magnetic systems escape us both in terms of accuracy and in terms of complexity. And there is still a lot of work to find powerful and accurate, let's say, functional theories for correlated systems. And that's some of the future work in this field. But if we stay, say, on this topic one of accuracy, just let me, pay homage for a moment to Walter Kohn and, a set of brilliant ideas. Kohn had so many actually brilliant ideas in many directions. Maybe he's very famous for density functional theory, but is by far not, not his single achievement. But let's focus here on density functional theory. The top 15 papers of the APS, the 12 papers in the top 100 from Nature. And his first statement was figuring out with the first Hohenberg and Kohn theorem that actually you can talk about a system, say a water molecule, by saying there are 2 protons, 1 oxygen nucleus and 10 electrons, and that defines uniquely what this system is. So the external potential, the 3 nuclei in the adiabatic approximation, and the number of electrons. But what he proved, say, with actually an ad absurdum proof, so a proof that was leading to say an absurdum if the hypothesis was true, was showing that actually there is a one-to-one correspondence between the description of a system through the external potential and the number of electrons, and instead the ground state charge density. So you can, uniquely define a water molecule in a specific configuration of the nuclei by saying there are these 3 nuclei here and 10 electrons, or instead talking about the ground state charge density in that configuration. One-to-one correspondence. Talking about the first is equivalent to talking about the second. But talking about the first is what the Schrödinger equation tells us. So, we have the external potential, we have the number of electrons. So we solve the Schrödinger equation for the many-body wave function. And instead, thanks to the one-to-one correspondence, what he showed is that one can actually determine a functional, the universal functional of density functional theory, that is a functional of the density. And I won't go through the theorem, but very intuitively, since the ground state charge density determines uniquely the system, at least in theory, it identifies what is the potential, what are the number of electrons, what should be the wave function that is the solution of the Schrödinger equation, and then what is this expectation value of the kinetic energy and the electron-electron interaction that is the universal functional of density functional theory. So we prove that it exists, but we just don't know what it is, and that's the great weakness, if you want, of density functional theory. It's very beautiful, it's very formal, but actually it doesn't give us a protocol, a procedure. We don't know what f of n is. We just know that it exists. But let's not lose faith. The next step is even easier. Again, I will not sort of prove it, but if you have this universal functional f of n, you can also write a functional for the total energy of the system that is just this f of n plus the electrostatic energy of the charge density in the presence of an external potential. And so all of a sudden we have turned around, the Schrödinger equation into a very simple variational principle where for an external potential, we would minimize this quantity with respect to a super simple object, the charge density that is just a real scalar field. No comparison with the exponentially exploding complexity of the ground state wave function. So if we had f, computational quantum mechanics would be trivial. I could solve on my cell phone, protein folding. Instead, it's still a challenge because we don't know what f is, and the brilliance of Walter Kohn and Lou Sham was actually inventing a way to approximate this f of n that was both very physical and actually very lucky. If you're not lucky in the world, often, you know, it's you struggle. But as Emily Dickinson said, luck is toil, so you really need to try hard, and then some luck arrives. So what did Kohn-Sham say? They sort of invented something that doesn't make any sense. They invented a system of electrons that don't interact. So whenever you study, you know, density functional theory with Kohn-Sham approach, that is what every one of us does. Remember, those Kohn-Sham electrons don't mean anything. But they were a trick to try and break down that unknown universal functional f of n in terms that were manageable. And so they defined these non-interacting electrons that live in a different external potential than, say, the potential of the true, say, water molecule. That's called the Kohn-Sham potential. And what happens, they said, well, let's construct this Kohn-Sham potential such that the ground state of the non-interacting Kohn-Sham electron happens to have the same charge density of the interacting system. So this entire, you know, slightly bewildering construction was due to the fact that at this point you could decompose this you know, very mysterious universal functional in three terms. You know, f is unknown, and what Kohn-Sham do, they break it apart into three terms in which the first two are unknown and the third is unknown. So this is, you know, just a game, basically. You don't know what f is, and you say f is 3 plus 2 plus unknown. So you would say we haven't made any progress, but the progress was made because the first two terms captured a lot of the, you know, energy functional. And as I said, they were somehow lucky for the third term. So the first term, T of S, is the kinetic energy. It's the quantum kinetic energy of the non-interacting Kohn-Sham electrons. So again, it's nothing to do in principle with the quantum kinetic energy of the true electronic system, but it turns out it's you know, a very decent relative. And in particular, we can calculate it because for the non-interacting system, the Slater determinant of the Kohn-Sham orbital is actually the exact wave function. So we can just take the second derivatives of those Kohn-Sham orbitals. If you have the charge density, in principle, you will think you have no clue of what is the curvature of the wave function, because the curvature of the wave function is obliterated when you take the square modulus. So by going back to this Kohn-Sham non-interacting electrons, there was a way to define a quantum kinetic energy. It's not the exact one, but this is the key step of the Kohn-Sham construction. And then they said, let's add to this universal functional, you know, some kind of model of the electron-electron interactions in terms of a Hartree electrostatic repulsion. And then we say everything else that is left is sort of, you know, swept under the rug of this exchange correlation potential. You know, if you were, you know, living in 1965 and you read the paper, you say, you know, this doesn't make any sense, or, you know, whatever. And in fact, you know, for, you know, 15 years, probably the answer was whatever. That is, it looked maybe interesting, but no one dared really to do anything. And it's only in the sort of late 70s that people started to try out things and figuring out that it actually could work very, very well. And the reason it works very well is that, you know, the physics built in this non-interacting kinetic energy and in the Hartree electrostatic interaction captures a lot of what F is. So the last term is very small, but actually the way they built it in the local density approximation captured some fundamental sum rules that, this term needed to satisfy. So they were also, I would say, a little bit lucky in all of this. Anyhow, this is my sort of end of the introduction of density functional theory. The power of it is that it's a functional theory. We have a functional to deal with the energy, with its derivative, all the materials properties that we can calculate it, and it doesn't have this explosion of complexity of the diagrammatic or perturbative approaches like Moeller-Plessé, couple cluster, many-body perturbation theory, and so on and so forth. For those of you that like these concepts, representability is trivial. Basically, any charge density is a good charge density. And just as a historical note, I want to contrast the density functional theory, where the functional, we know that it exists but is unknown, and on the other hand, the representability is trivial, with a reduced density matrix theory, where actually the energy functional is known. We don't need the Schrödinger equation to calculate the total energy exactly, because in the Schrödinger equation there are only one body terms and two body terms. So we only need what are called the reduced density matrices, the first order and the second order, that are just the integral of psi star psi on all other variable apart from 2 or apart from 4. So in reduced density matrix, actually the functional is here is trivial, but we don't know how to search because we are not able to search in a space of 4 or actually by 3 12-dimensional gamma 2 reduced second order density matrices that make sense. So any function gamma 2 that you write doesn't make sense in general, while every charge density that you write makes sense. So let me actually focus now on the topic of this talk, that is what are the weaknesses of density functional theory. And the functional exists, we don't know what it is, we approximate it, and in this approximation we make errors. Some errors are small, some errors are big, some errors are catastrophic. And so a discussion on these errors will be what comes next. But also remember, and this is very important, is a theory of total energies. We say it's a static theory that is just depends on an object that is static, is not dynamic, is not frequency dependent, it's local. And from a static theory, you cannot get excitations. And also in all of this, remember that the energy level of the Kohn-Sham electrons have in principle nothing to do with the electronic excitation of our system. The Kohn-Sham electrons are just a trick to get the quantum kinetic energy, at least approximately. There is something that I'll come later that has to do with the differential equations of density functional theory in the Kohn-Sham formulation versus the Schrödinger equation, that actually means that the highest occupied orbitals in these two theories, of course in the Schrödinger equation is exact, but also in density function needs to be exact, because it determines the asymptotic decay of the charge density. And because the charge density in exact DFT is exact, the asymptotic decay needs to be exact, and so the HOMO needs to be exact. Let me actually sort of tell you a little bit of the failures of this. This is a 30-year-old movie I'm very fond of. This is the dissociation of a chlorine molecule on an aluminum surface. And what happens as this molecule comes close to the surface is that we have a charge transfer from the Fermi energy of the metal to the LUMO of the molecule. And once you have 2 electrons fill the LUMO of Cl2, Cl2 minus minus want to explode. So you have a cannonball dissociation on the surface. And this movie is wonderful, but is also completely untrue. This is not what happens in reality. This is what happens in, say, density functional theory. And the reason why this happens is that the LUMO is in the wrong position. And in principle, in exact density functional theory, you would have that as soon as an infinitesimal fraction of an electron transfers to the LUMO, that LUMO would jump, would become the HOMO, and it would become exact, and so it would all be okay. And that's what actually the derivative discontinuity of the exchange correlation potential is. But in approximate DFT, this is wrong. So this entire simulation is completely wrong. It's still very beautiful, so I shouldn't discount it. And, you know, things are actually so complicated in what is, you know, exact density functional theory. And these are sort of, you know, model calculation on simple, say, one-dimensional systems where you can actually solve the problem exactly. But here, Nipa Mitra and Nicole Helbig are actually dissociating a very simple model dimer. And as you see, as you go at further and further distances, as you go towards 10, so you are dissociating your molecule, the Hartree exchange correlation develops one of these needed discontinuity in the middle of nowhere. So you are breaking apart the molecule, and in the middle, where there is no charge density, the exchange correlation potential needs to become singular in these weird ways. And so you can see very clearly how difficult or impossible to make exchange correlation approximation that fix this problem. Other sort of, you know, flavors of failures, it tends to delocalize electrons a lot. So whenever you have, say, a self-trapped hole or a self-trapped electron, here we have a hole that should be self-trapped on one of these thiophens, and instead is completely spreads out, and then the physics of the binding of this thiophen is completely wrong. Or as I told you, in principle, in exact density functional theory, the HOMO should be exact, and so the ionization potential that is opposite of the HOMO should be exact. But if you compare, say, experiments with, say, LDA, GGA, one of the standard functionals, you could say the trends are right, but, you know, the errors can be of 10 electron volts. So, you know, it's completely useless unless you really want to know what is the change in HOMO and going from one material to the other, but the absolute value is completely off. And actually, and probably this is the most important concept I want to pass you, is that, you know, this theory that gave, you know, Walter Kohn the Nobel Prize, and is really a, you know, reformulation of quantum mechanics, can fail even for a one electron system. You take the simplest molecule, one electron binding two protons, H2+, you dissociate it, and you know, for this one electron problem, this is what the Schrödinger equation looks like, and these are what the Kohn-Sham equation look like. And you know, these two solutions are not going to be identical unless the Hartree and the exchange correlation would cancel out exactly as for a one electron problem Hartree-Fock would do. Hartree and Fock terms would cancel out. But Hartree and exchange correlation don't cancel out, and actually what happens in most approximations is that Hartree dominates. And so what happens is that because of the Hartree self-interaction, the electrostatic interaction of the electron with itself, what that VH potential wants to do is wants to smear out the electron as much as possible. So you dissociate this molecule, and for every distance there is only one sort of lowest energy solution where the electron is smeared out, and by the time you have completely dissociated, you have half an electron on the left and half an electron on the right. Now, this would not be so bad in principle, because the exact system, the Schrödinger equation, has a left-right degeneracy. So in the Schrödinger equation, the solution with an electron on the left is degenerate with the solution with an electron on the right, and thus any linear combination of these two solutions is a good solution. So Kohn-Sham theory gets a wave function with an electron split that is actually not a bad wave function, is a good wave function, but what is terribly wrong is that it's the only wave function possible. There is no left-right degeneracy, and actually, as you'll see in a moment, the estimate of the energy on this wave function is extremely poor. Now, well, let me actually show you what happens. This comes from work of Aaron Cohen and Paulo Sanchez and Rita Young. You see, the dissociation of H2 plus would give a red potential energy surface if we solve the Schrödinger equation, or for a one electron, Hartree Fock is exact, so that's red is the correct one. But say density functional theory in black, say in the LDA approximation, fails miserably at dissociation. And if you are very smart and you use a hybrid functional, a regular one, there are more sophisticated hybrid functional that probably Professor Kronig will mention later. But if you use a standard hybrid, you mix LDA and Hartree Fock, and what you get is blue that doesn't look very good. And what is wrong is that this limited dissociation is very, very poor. That is, the energy of the proton with half an electron on top is much, much lower than what it should be. And so we often talk about, and that's the super important concept, the fact that we have, I don't really like the term delocalization error, but we have a lack of piecewise linearity in the total energy as a function of occupation. And what does it mean, a piecewise linearity? It means that if I take a dissociation, say 1/10 of an electron from the left, the energy cost I pay is equal to the energy gain that I have if I put that 1/10 of an electron onto the right. So if the energy of this subsystem on the left is linear as a function of the electronic charge density, then the cost of extracting anything from here will be exactly counterbalanced by the gain that we have by putting the electron on the other side. So having piecewise linearity on the subsystem enforces this left-right degeneracy. And this is the most important concept of this class, of this lecture today. And you could think that H2 plus is an exotic problem, but this happens all the time. You'll see in a moment a cathode material for a lithium-ion battery where the iron might want to be 2 plus or 3 plus, so the electron doesn't know on which iron to sit, and if our functional has this, we call it self-interaction error driven by the Hartree functional, is not going to be able to reproduce reality. So how do we restore piecewise linearity? That is actually an exact property of the total energy of the system. So it was already proved by Lieb and by Levy and Perdue in the early 80s that in general the total energy of a system as a function of its total charge density should be piecewise linear with respect to the number of electrons. Well, what happens are, I think, two very important things. One is that there was something called Hubbard corrections to density functional theory that was developed by Anisimov and co-workers in the early 90s. This is wonderful, is derived from the Hubbard model, but it very interestingly, it does the right thing for at the end what was a wrong reason. So the physics that the Hubbard correction embody have nothing to do with correlations. When you look at this Hubbard correction, in particular, in what is called the rotational invariant form that Sergei Dudarev and co-workers have introduced, that is basically a strength, and then we are using these matrices that are just projecting the Kohn-Sham states on atomic orbitals. So we are looking at the population of, say, an atomic manifold like the 3D orbitals of iron. What this term is doing is really in the form of occupation times 1 minus occupation. So it's removing a term that is quadratic in the occupation and is adding a term that is linear in the occupation with a certain strength U. So what this rotation is really removing quadratic dependence as a function of occupation that is present in approximate red DFT, and is removing that quadratic term and putting instead a linear term, so that the DFT plus Hubbard U aims to match the exact piecewise linear behavior. The two important statements at this point, one was the first sort of, brilliant insight from Matteo Cucoccioni that understood that the strength of this correction is really related to the second derivative of the energy. So the U is not some whatever mysterious fiddling parameter that you get from the PhD student that preceded you, but is actually a second derivative of the energy with respect to occupations. And so we can calculate it formally, as you'll see in this class, with a linear response theory. So that's the first step, crucial. The second step is now also extremely important, but it's an approximation. What we are now saying is that we want this piecewise linearity enforced by this DFT plus U term, not on the total energy on the system, but on the energy of a subsystem like the 3D electrons of an iron, of a transition metal atoms. This second step is a heuristic guess. It's an approximation. It's saying it should really happen. And it really needs to happen. And the reason it needs to happen is that even in a solid, atoms are still atoms, especially the localized electrons of a transition metal, of a lanthanide, of an actinide, really keep all their atomic physics and atomic complexity. We'll see a bit later what happens. And the most important thing that they are missing when they are thrown into density functional theory is that lack of piecewise linearity that would enforce, say, the left-right degeneracy in the case, you'll see it in a moment, of a mixed valence system. But remember, this is a heuristic assumption. So in some way, the DFT plus Hubbard correction have nothing to do with correlated electrons and are an approximate way to enforce piecewise linearity on a localized manifold. Now, correlated electron systems have a lot of localized electrons. And so DFT plus U helps a lot the description of correlated electron system, but it doesn't have anything to do with correlation. And you can see this very clearly in this example. Say this is a mixed valence olivine. In this unit cell, we have 2 iron atoms. And what we are looking is we are changing the occupation, the charge density of one iron atom, and we are looking at what happens on the second iron atom in red. Nothing is happening. There is no Hubbard model physics here. The Hubbard model physics is one where you have sites and occupation, and double occupation on a site, they hate each other. Here, our DFT plus U formulation is completely oblivious. Once, the occupation on one iron atom changes, the other iron atom is completely untouched. Because in the Hubbard model, there is no other way than for the electrons than to sit on the Hubbard sides. In DFT plus U, actually what happens as you change the occupation of an iron, you actually change the population on the nearby ligands of the oxygen. So these terms controls and regulates the charge transfer between the localized electrons and its neighbors. But once you put it under control, you can actually do very well in describing system with very localized electrons. And to show that, DFT plus Hubbard has nothing to do with correlation, already, 15 years ago, with Eder Kulik and with Matteo Coccoccioni and with Damian Shirley's, we showed that, DFT plus U can do great things, not only in solids, but in molecular system. At that time, it was anathema. And we did something very interesting that is, I think this was one of the very first time in which we did super accurate quantum chemistry calculation with multi-reference configuration interaction and compared those with density functional theory for a very simple reaction. This is an example saying which methane transforms into methanol thanks to the action of a catalytic center that is iron oxide plus that inserts this red oxygen into the very difficult bond to break, the carbon-hydrogen bond. This is a very fascinating reaction. If you think at black as being the exact quantum chemistry curve, you enter the system as a sextet, you exit the system as a sextet, but the most important barrier is a quartet. And so even if the reaction is exothermic, the reaction rate is very, very small, because in order to go through this barrier, you need to go from sextet to quartet and to sextet again. So it's driven by spin orbit coupling that is very weak in the system. And if you do this calculation with standard GGA, you get these blue curves here that look good, but they are a couple of electron volts off. So you're not going to do any chemistry. You switch on the U, and actually it looks very, very good. And this to me was the first demonstration that the DFT plus U is actually a theory of self-interaction, of piecewise linearity, has nothing to do with correlation. Then Matteo kept thinking and actually figured out a refinement that is much smaller but can be extremely important. You'll see in a moment, in which what he was thinking is the original rotational invariant U removes this quadratic dependence, put back the piecewise dependent, and really tries to restore as much as possible integer traces here, either 0 or 1. But somehow it can push the system a little bit too much through the atomic ionic solution. And so it's actually very good to have it counterbalanced by off-diagonal elements that we call intersite V-terms between the localized manifold and the ligands that balance this tendency to render the system more atomic. And again, these can be calculated fully from first principle. You learn in this class how to do that. And if you want, once you add these terms, again, in a sort of sketch, is that not only you restore the piecewise linearity, but you bring your energy functional closer and closer to the exact functional. And at this point, things started to look very interesting. Very soon, Matteo sort of gave us his code, and with Eder Kulik, we started to look at some very interesting molecules. I was fixated and still fixated with molecules. You see this seesawing transition metal dioxides. These are, you see, 3-atom molecules, manganese or iron on cobalt, that in DFT would be bent, and this is the angle that they make, and DFT plus U, they would be linear, and they are linear because the U really weakens the covalent bond too much. And in reality, some of these are bent, some of these are linear, but the DFT plus U plus V approach of Matteo would actually reproduce both the bending and the linear term. And it's something that really counteracts the tendency to break the covalent bond. You could see that if you actually forced the system not to break the bond, and again, this sort of sequence of angles would be preserved. But of course, DFT plus U plus V does it without forcing anything on the system. And, you know, now, and I conclude the Hubbard, and then I'll do the brief introduction to Koopmans. I know that we need to have questions, and we have still 15 minutes, so I'll try to be short, and probably will compress the questions a little bit. We can answer them on Slack as well. But, you know, let's take a, you know, poster child for this piecewise linearity problem. That is system where the transition metals needs to change oxidation state, exactly as it happens in a cathode materials for a lithium-ion batteries. This is an olivine, lithium, you know, iron, lithium, cobalt, lithium, manganese, phosphate is the transition metal. You know, we cycle lithium in and out. The oxidation state of the transition metal needs to change. And, you know, with Matteo, we saw, you know, a few years ago that actually, if we looked at the system in the fully lithiated case, in the fully delithiated case, and in the mixed case, when in the mixed case, half of the transition metals needs to be in one oxidation state and half of the transition metal need to be in the other oxidation state, whenever we added the full DFT plus U plus V treatment, we could see in the mixed valence system ions that looked exactly as the ions in the fully lithiated system, the 2+ ions, or exactly as in the fully delithiated system. You see, even more remarkably for the case of manganese. So the manganese 3+ looks exactly, this is the population as the manganese 3+ in the delithiated state. While if you just use DFT, you see there is no contrast, there is no difference between the 2+ and the 3+. The self-interaction smears the electron identically. And the representation of oxidation state, this actually just came out, is printed now in PRX energy, can be seen in even more complex cases where we take mixed olivines, iron and manganese, or we look at intermediate concentrations. But if you look at the charge on each ion, you see in the DFT plus U plus V, that is the last line here, you see these digital changes. It's either 3+ or 2+, the manganese, the iron, even the mixed system, first the iron changes, first the manganese and then the iron. In a standard DFT, is just a linear soup. You see there is no contrast, you know, there is a linear increase in the oxidation state. Hybrids do a much better job, but you see they're still imprecise quite a bit compared with, say, DFT plus Hubbard. And you see that in the voltages that, you know, DFT plus Hubbard plus U plus V predicts the light gray voltages compared to the experiments, that they are much, much better than the red DFT voltages and quite significantly better than the hybrid voltages, and in particular for the right reason, doing the oxidation states. And this extends, maybe I should skip this, also discussing, you know, the energetics of vacancy. But in all these systems with localized electrons, I think right now, these DFT plus U plus V approaches are best functional for electronic structure simulations. There is still a major failure of this, that is, we only, I think, do very well for systems that are in what the chemist would call a single determinant configuration, the high spin states. The multiplates, the multi-determinant configuration, I think are just beyond even these functionals, and I think are one of the future direction where to figure it out. Yuri will give you an introduction of, you know, the beautiful work that he has done to use actually density functional perturbation theory to calculate these coefficients very efficiently, accurately, and straightforwardly. So these days they can be used very easily in calculations. And maybe I should stop here the Hubbard part and spend 5 minutes on the Koopmans functional, and then conclude. I have here actually maybe a summary of what we are doing with say dft plus u or dft plus u plus v, where we really sort of take into account the very strong self-interactions of localized orbitals and also the interactions with the nearby ligands. There is much more work that is coming on the correlation effects with functionals on these orbitals, but of course correlation is also what very expensively dynamical mean field theory does. And some of the very interesting works of the recent years come also from Alex Zunger in substituting dynamical theory with supercells, and that's also another very interesting direction that I think there is just no time to present in this talk. So let me conclude with the fact that on sitting on the enthusiasm for what we had been doing with DFT plus Hubbard, I think, and this is maybe now sounds arrogant, but I had asked a PhD student in the group at that time to generalize DFT plus U and apply this linearization correction to all the orbital in the system. And what we have understood during the years is that what we were actually going to achieve, and this is what I'm presenting here, is that we were actually going to generalize our functional theory to be not anymore a theory of total energies, but a theory of excitation, a theory of spectral properties. But to become a theory of spectral properties, it couldn't be anymore a theory of a static local functional, as it is density functional theory, but it needed to be more general, and in particular it needed to be a functional of a dynamical object of the spectral density. So an object that is local but is still dynamical. And actually the spectral density becomes very intuitive when you think at it in a quasi-particle approximation. Only certain omega becomes engaged, and these are nothing else than the orbital density. So by going from a static theory of the local density to a dynamical theory of local orbital density, we could actually predict spectral properties. How do we do that? Well, we started from this assumption again. We want piecewise linearity with respect now to every electron that goes in or out of our subsystem or of our entire system. And this piecewise linearity on the energy translate in the expectation value through Janak's theorem of the Hamiltonian on the single particle orbital being a constant. So this requirement is our own definition of self-interaction, and it's actually very intuitive. You see, if an electron doesn't interact with itself, you want this expectation value to not depend on the occupation of that orbital. Not only that, but if you think this is reminiscent of a photoemission experiment where you remove an electron from an orbital in the system. So how do we enforce this piecewise linearity of the energy with respect to the occupation of every orbital? That is, how do we enforce that this expectation value for the single particle energies are constant? It's very simple. Exactly as in DFT plus U, what you do is that orbital by orbital, you remove the actual dependence of the energy on the occupation. That is roughly quadratic, but this is what explicitly is the dependence of the energy in the occupation of the orbital Fi, and you substitute this pseudo-quadratic dependence with a linear dependence. That is what we call the Koopman's term. So you see the second term that we add is linear in the occupation Fi, and the only question is what is the slope? What is the eta I? And it's very simple to actually take as the slope, you know, the difference in energy between the two extrema. Actually, density functional theory does a very good job for the energy at integer occupations. And so this integral of the expectation value is nothing else than the energy at occupation 1 minus the energy at occupation 0. So this is the entire concept you want to have. You know, this spectral functional, this Koopman functional, linearize the density functional theory energy orbital by orbital, removing the quadratic term and adding a linear term. There is one simple statement that you discover from this, and that is the K functionals, these Koopman's functionals, actually at integer occupations, if Fi is equal to 1, these two terms cancel out. So this functional have the same exact value as the Ft at integer occupation, but they are completely different and they are piecewise linear at fractional occupation. So the total energy at integer charges is the same. So they don't actually change our potential energy surface, but they change our spectrum. They change our derivatives. And the last piece of information that you need is this, when it's used as a functional, what we'll have is that actually it will have the response of these orbitals to the process where we are changing the number of electrons in that orbital. And so we actually needed to screen it properly to take into account this relaxation of the Fi. The previous functional was working at frozen orbital. Instead, we need a relaxation. And this relaxation terms is a little bit like W, is a screening term. Now, I realize I've gone well beyond the space, time allotted. So let me actually basically conclude here, just telling you that these functional are actually in practice very, very easy to use. You learn in this class how to use it. We have two flavors, the Koopman's functional that I've just described, that, as I said, at integer occupation doesn't touch the total energy of our system. And then we have a Koopman's functional where we also add a self-interaction correction that is a screened Perdue-Zünger term, and that also is going to improve the total energies. And in practical calculation, that's what you learn. You have to minimize this functional, you have to calculate the screening coefficients, but the results can be remarkably good. Ionization potentials in molecule are basically, almost a state of the art. Photo emission spectra you see in red experiment versus the KIPZ functional for molecules look very, very good, and there is no alignment of the peaks here. It's what comes from the simulations. Even at different energies, all these peaks come out well. Even very difficult affinities that not even quantum chemistry at the couple cluster single, double, perturbative triple can get actually very accurately. I won't go into these details. And maybe let me conclude, and this is, very much also fits in the next talk about Leo Kronig. There are a lot of, synergies and resonances here with the work that they have been doing and the work of many other colleagues in the field. Let me just conclude with maybe one statement that as we go in the solid state limit, this functional keep working very well because the orbitals that minimize this functional are actually localized. They look like Vanier functions. And so the system that linearizes the energy of the electrons going in and out of this localized functional doesn't know if it's a molecule or in a solid. And so we go to the thermodynamic limit of an infinite solid, very smooth. And actually, the band gaps look very good comparable to state-of-the-art. You see, quasi-particles are consistent GW with vertex correction. Not only the band gap are very good, but actually the alignment of, say, in this case, the top of the valence band with the vacuum level is much, much better than GW. And you can see, but you'll see in the next talks also some of the examples of band structures here. I think I'll just finish. I think the conclusions are here on linearity and screening and localization. If you want to know more, there is a review that we have written with Andrea Ferretti and Chris Wolverton on all these methods. And let me thank all the people from the early work with Ismaila, Matteo, and Andrea, but in particular, Yuri Timrov has been in the last few years a pillar of this work on Hubbard functionals, and Nicola Colonna, Edward Linscott, and Riccardo De Gennaro for the Koopmans function that we'll see. And I think I just thank you all and apologize profusely for having gone even overboard. Thank you.
Thank you very much, Nicola, for the very broad and inspiring talk. We have some questions from attendees, so I will read them from Slack and propose them to you. So the first question is, what explains physically the energy being piecewise linear, not piecewise constant, given the discrete nature of the number of electrons?
So what we are thinking at it is, if you want a statistical mechanics description, so we are not going to describe one system, but we are going to describe an ensemble of systems. This is how Lieb and Levy and Perdue discussed this piecewise linearity, that is making sure, if you want, that if I have, say now, one hydrogen atom here, one hydrogen atom here, one hydrogen atom here, and one hydrogen atom here, but I have only 3 electrons, the total energy of the system made sense, having a sort of size consistency in this problem. So in a nutshell, it's really an ensemble description of a system with identical replica, but with a number of electrons that is not equal to the number of atoms. That's how you build the piecewise linearity.
Okay, thank you. Following question is from Marco Boscovic. I hope I pronounced the names correctly. Is it possible to find the exact exchange correlation functional by taking experimental results? For example, measure electron density with scanning tunneling microscopy, and then use some algorithm for reverse engineering. Yeah,
so I think the experimental results are too few to figure out what is an incredibly, as it's called, ultra non-local, and I would call a barking mad exchange correlation potential. So the problem of the exchange correlation potential is that in the sort of exact case, it has some very, very weird properties. So we don't even have the analytical form to describe it. There have been efforts, say, many years ago by Kieran Burke in looking at one-dimensional system and see if it could be machine learned. But I think anything that has a derivative discontinuity is something that we are going to have trouble to learn. So the problem is that even with a lot of data, we wouldn't be able to capture, I think, some of these properties. And my belief is that we need to go to dynamical exchange correlation potential, dynamical self-energies that are much better behaved.
Thank you. So we have more questions. I will read 2 more, but the other ones, since they have a technical nature, I recommend the person who are asking them to keep them for the next days, so they will have a chance to ask them again and get some answer. So the next question of more general character is this one by Gokharan Shukla. If U parameter does not count correlation energy, I guess it started to play after half occupation of orbital, then what does it count? I guess means what it represents.
So
what is physical? Yes?
I didn't understand the first part of the question.
So the question is, if the U parameter does not count correlation energy, then what does it count? And what is the physical meaning of V in DFT plus U plus V?
Yeah, so it's really a self-interaction energy. So it, say in a one electron system, the U parameter does what Hartree-Fock does with the Fock term. So it combats, the drive of the Hartree potential to delocalize the electron. So it fights the electrostatics. That's what the U parameter does. And that's also what the V parameter does. It tries to balance this, chemical interaction, not only on-site, but inter-site.
Thank you. So I'll pass on the last question. What was this? Okay, so this is the general question. What is the computational cost of Koopman functional or GGA plus U or meta GGA compared to these other meta GGA hybrid GW approaches?
So in a GGA plus U, if you have a U, the cost is negligible. It's zero, I would say. Getting the U requires a linear response calculation that is expensive, but you'll also see some work from Martin Hurin on actually how easily and powerfully you can actually predict it from machine learning methods. In the Koopmans, it's a little bit the same story, but now you have a lot of parameters, one for orbital to learn. And so the cost is again in the screening, what would be the W in GW. There is an additional cost that the functionals are not anymore invariant for unitary rotations, but the real cost is the calculation of the parameters. And again, you'll see work from Edward Linscott and Yannick Schubert on machine learning those parameters. So the cost is always in the linear response calculations of these parameters. That's also why these systems are, why these methods are accurate. But I think we are seeing in the last year a lot of progress in actually machine learning these parameters because they encode a very simple chemistry, I would say.
Okay, thank you very much, Nicola, for your very nice and inspiring talk, and thanks also for taking these questions. We have in program some coffee break that I guess we can compress to a few more minutes. We thank Nicola again, although it's only virtually. And
no, thanks to you all, and thanks Matteo, Yuri, and everyone for the organization. And I look forward to the next lecture.